everybody, welcome. Thank you so much for joining us today. My name is Kelsey, and we're going to be working through some geometry problems as they might show up on the SAT or the ACT. So whether you're just joining us for the first time or you've been hanging out with us for a while, we're here every week. I'm so excited that you've decided to give about an hour of your summer to practicing some math for these tests that might be coming up in your life. So if you're ready to get started, go ahead, grab a calculator, grab some scratch paper. We're going to do some geometry problems and start to think about how we can use some strategies to make these problems a little bit easier to digest on these standardized tests that we might see. So let's just get started and dive right in. This is a really typical looking word problem that might show up. And this one is an ACT problem. You can tell that because there's 5 answer choices. On the SAT, there's only 4 for the multiple choice. On the ACT, there's going to be 5. And also ACT is the one that kind of alternates A, B, C, D, F, G, H, J. So that's how you can tell the difference between the two tests. This is an ACT word problem. And it's number 14. So if you remember, if you've taken an ACT officially or practice test before, you know that there's 60 math problems to do in 60 minutes, and they increase in difficulty as you go along. So you can kind of tell what the ACT considers to be an easy or a difficult problem based on what number it is. So this one's number 14. So this would be one of the easier problems, but we'll see how it's still got some components that might make it a little bit tricky for us to tackle. So let's just give it a shot here. It reads, an office building has the dimensions in feet given in the figure below. What is the area in square feet of the building? So there's a couple of different ways that we can approach this problem. And one of them is just if you happen to recognize the shape that you're dealing with and you remember the formula that you need to be able to calculate the area of that shape. So let's try that one way first. Let's see. So we recognize that this is ultimately a trapezoid. So we can just remember what the area of a trapezoid is. Anybody know that off the top of their head? That's going to be the area is equal to, is 1200 the base of the entire figure? Yeah, this isn't really great labeling, but that's what this indicates. The 1200 is going all the way across. Great question. The formula for area of a trapezoid is going to be 1/2 base 1 plus base 2 times the height of the figure. So base 1 being, I guess, this 800, base 2 being the 1200, which goes all the way across the bottom. And now it's a little bit of a plug and chug question, right? So the area is going to be equal to 1/2. Plug in those two bases that we have, so 800 and 1200. And we even conveniently have the height, so we can just plug all those numbers in. And if you remember with the ACT, you get to have your calculator for all the math questions. It's always a good idea to set them up on paper, but you can use your calculator to solve this one out. This is going to be equal to 1/2 800 plus 1200. That gives us 2000, right? And then 1100 over here. And calculate that all the way out. That's going to give us 1,100,000 and 3 zeros right there. And I have just noticed a small typo in this. I thought I fixed this. Sorry about that, guys. This should be 1,100,000. So that should match up there. So if we were to remember the area of a trapezoid and just be able to plug and chug, that would be a pretty straightforward way for us to get to the answer here. But unlike with the SAT, the ACT doesn't give you a formula bank. So you would have had to have that formula memorized. It's not going to give you any sort of formula sheet at all. So let's look at how we might be able to tackle this question if we didn't remember that formula for a trapezoid. So let's try another way. Let's break it up into pieces that we know how to calculate it. So this is going to look like we've got a couple of different pieces here. Let's start with the easiest one, which is going to be we've got this square or rectangle, I guess, situation going on here. We've got 800 along the top, and then we know the height. So let's go ahead and calculate that chunk before we deal with the chunks that are maybe a little more complicated. So we remember that the area of a quadrilateral of a rectangle is going to be equal to the base times the height. So that's going to be equal to the base of the thing is going to be just 800. That small base that we have. And then the height is 1,100. So that is going to give us, again, we've got our calculator for this one here. This is going to give us 880,000. Okay, so we're not done. Obviously, we need to calculate these other chunks that we didn't get the area of when we got the area of this rectangle in here. So let's remember what our formula is for area of a triangle. Again, something we need to have memorized, but something that might be a little bit easier to pull out than the area of a trapezoid. The area of a triangle we know is going to be equal to 1/2 base times height. So let's think about what the base, let's just look at this triangle on the right here. We know that the height is going to be 1,100, but how do we calculate what this base is? Well, we've got the pieces, we've got the right pieces, we just have to put them together. If this whole thing on the bottom is 1,200 and this piece here is just 800, we can figure out what the other legs are. If this is 800 here, then down here we need to have 400 split between the two legs. So this is going to be 200 and 200. So now we have what we need to be able to calculate the area of one of those triangles. So that's going to be equal to 1/2. The base we know is going to be 200 now. And the height gives us 1,100. And so to calculate the area of one of those triangles, that's going to give us 110,000. But we have two, remember? So we need to do both of those. We need to remember to multiply that by 2, and that'll give us 2,200, 220,000, excuse me, and then we want to add that back to the area of the quadrilateral that we got. And I see a question, couldn't you just ballpark through POE and narrow down to 2 choices? Absolutely. That was going to be my next point. So you can do all this work, or you can eyeball it and see if you can eliminate any answer choices that definitely don't make sense. And that's really the beauty with geometry questions, because on the ACT, they're all multiple choice, and sometimes it's a lot easier to spot a wrong answer than a right one, even before you've done any math. So let's take a look and see if any of these answer choices wouldn't have made any sense, even before we did any math at all. 3,960 is going to be way too small of an area for any shape that's got, a height this big and bases this big. Like, we could have eliminated that right away. And same deal, depending on how comfortable you are ballparking area, probably 120,000 could have been too small too. And so, that's always a good trick to have in your back pocket in case you forget a formula or in case you're running out of time to work on a problem. It's always a great idea to try to ballpark out answers that just won't make sense and guess between the ones that remain. It's definitely a totally legitimate strategy. But a couple, as with every question on this test, there's a few different ways to approach it. And so I like to show different ways because everybody's got a different style with these tests. But that's it for number 14. We're going to move on to another question here. Looks a little different, but it's got the same idea. So you want to be labeling the figure if they give you one, and if not, then you want to draw your own. Always write down the formulas that you think you're going to need, and that kind of helps you to frame your mindset. Usually your high school math teachers are asking you really straightforward questions like solve for X or find the area of Y. But as you'll see with these word problems, there's a bit of critical thinking involved. You need to keep your reading comprehension on high alert as you're working through all these math problems. And sometimes they'll give you weird pieces of the geometry that you don't expect to be able to put together. So putting those formulas down on your page is definitely going to help you to put the pieces together. So let's see how we might be able to do that with something like number 51. Again, this is getting closer to that number 60. So this would be a harder math problem according to the ACT, the people that write these tests. So we want to keep that in mind as we're working through here. This one reads, a regular hexagon is inscribed in a circle with a circumference of 6 pi. What is the perimeter of the hexagon? So first thing we're going to do is draw this. And it doesn't have to be beautiful, but it needs to be kind of down on the page so we can understand what we're looking at. Okay, so we've got a circle, and let's give ourselves some sort of a hexagon here. Doesn't have to be pretty. Remembering that a hexagon has 6 sides. Okay. So we have a regular hexagon inscribed in a circle. So this question already starts to read like a vocabulary question. We need to know what all these words mean. A regular hexagon is inscribed. So inscribed means that it's put inside the circle, just like this. And regular means that all the angles inside the hexagon are going to be the same. And so we should probably remember that that information might apply to this question and calculate what those angles are. So does anybody remember exactly how to calculate how many angles live inside a hexagon? There's a couple of different ways to figure that out. If you remember, a triangle has 180 degrees inside, a quadrilateral has 360, a pentagon has 540. Each time you're adding 180 to those numbers. And so a hexagon has 720 degrees. And so we can calculate how many degrees are on each side, right? 720 divided by 6. And that's going to give us the degrees in each side. And so we'll hang on to that for a minute. And also remember what our formulas are that we're going to need for this. So we see that we're given the circumference of the circle, and we're looking for the perimeter of the hexagon. So let's figure out what we can do with that circumference. We need to know the formula for the circumference of a circle, which is going to always be 2 pi r. So given that the circumference is 6 pi, we're going to be able to find that radius, right? 6 pi is going to be equal to 2 pi r. So we can eliminate the pi, divide by 2. And so our radius is going to be equal to 3. So how can we use that information to help us to calculate the perimeter of the hexagon? Well, let's just draw something in there and see what it tells us. So if we draw in this radius, and we know that that's going to be a value of 3, well, that's pretty interesting because it looks like no matter where we draw to the corners of this hexagon, we're going to be getting value of 3 here. Pretending that this is drawn to scale, of course. So pretty interesting stuff here. We've got basically 6 equilateral triangles in here because we've got a regular hexagon. So keeping that in mind, we can kind of fill in the rest of these sides. If all of these sides are going to be equal to 3, then we can just calculate the perimeter. The perimeter is adding up all the sides of a shape, and there's 6 of them. So 6 times 3 is going to be equal to 18. And we see that that's our answer here. Again, a way to ballpark with this question, if we know that the circumference, if the area or the distance around the circle is going to be about 6 pi, yep, exactly. That is exactly right. But we could have ballparked this too. If these are pretty similar numbers, we're not going to expect the distance around the hexagon and the distance around the circle to be vastly different numbers. So we could have ballparked out anything that wasn't pretty close to 6 pi. And remembering that the distance of pi, or the value of pi, is about 3.14, that could have helped us eliminate pretty much everything but D and B. And then we would have had to do this math to be able to narrow it down. But always good to look for opportunities to not have to do as much math as you think you do. So that's just another way where they're giving you weird pieces of the puzzle, putting shapes on top of each other that you're not used to seeing, but it's really no big deal. Once we kind of do our scratch work, we don't try to do too much in our head, and we just work through kind of methodically with the pieces that we're given. So let's try that out on an even scarier looking problem. A lot of students get kind of freaked out by 3D geometry in the SAT and the ACT because maybe you haven't done a lot of it in your school. But I just want you to remember that all the same rules of 2D geometry apply here. They're always going to give you the pieces that you need to be able to do it. Okay, we want to go back and see where we got 720. So I was just saying maybe we were going to need that, but we ended up not. When they say regular, that means that all the angles are going to be the same inside. And so just in case we needed to know what those angles were, I, basically added 180 to all the shapes. So we know that a rectangle has 360 degrees. You add 180, add one side, that gives you a pentagon, which has 540 degrees. Add 180 on top of that, and that tells you how many degrees are inside a hexagon. So that's something you can kind of do on the side if you've got those bigger shapes that you don't know off the top of your head, how many degrees live inside. Okay. But moving on to 3D geometry, they're always going to give you the pieces that you need. So you just want to follow the same approach as you would for a shape. Okay, going back there, another question. Good. Glad you guys are paying attention. How did we know the third side is a 3 if it's not a radius? Because these are all equal-sized angles in here, because we know that it's a regular hexagon. This word tells us that this thing isn't going to be, flatter or wider than it is. So all the angles have to be the same. Super good questions, you guys. Anything else on this one before we move on? Okay. Love the good questions. And something I want to point out on these questions is often you might see information showing up in a word problem that you don't need to solve the problem, especially on SAT math. They love to throw in extra details that you don't need. But whenever they give you a note, they're not so diabolical that they're going to give you a note to throw you off into some random direction that's not going to help you solve the problem. The notes are always helpful. I can't say the same for everything that they give you in the word problem itself, but the notes are always helpful. So that's something really important to keep in mind as we work through this problem. So this is a number 41, probably one of the harder ones you would see on ACT. And it says that a gallon is 231 cubic inches. Which of the following is closest to the area of the base in square inches of a pyramid-shaped container shown below, with a height of 15 inches and a volume of 2 gallons? All right, and then it gives us this formula, which is really nice. On the ACT, they won't give you the basic formulas, but they're not going to expect you to know the volume of a pyramid off the top of your head. So they're going to give that to us in a note, which is helpful. So let's just take a step back, take a deep breath, and find an easy place to start doing something to make progress with this question. We know that this thing has got 2 gallons. So right away, they're trying to throw us off because it said that 1 gallon is 231 inches. So we want to make sure that we're reading really, really carefully and that we catch that. And so let's figure out how many cubic inches are actually inside this thing. So if 1 gallon is 231, we just want to multiply that by 2 and figure out what we've got going on here, which is going to be 462 square inches. Cool. Now we've got to get into a little bit more of the weeds here, but let's just write down that formula. This is my favorite way to get started on a question that doesn't seem obvious, is just to write down the formula without plugging anything into it. So it tells us that the volume of a pyramid is going to be equal to 1/3 base times height. Okay. So let's think about which pieces of this equation we have. We're looking for the base area, which is going to be like the area of the quadrilateral that's down on the bottom here. But we have the volume and we have the height. So let's plug in what we have and solve for what we don't. So what we have is the volume, which is going to be 462. And that 1/3 is just going to hang out in there. The bases are unknown. That's what we're looking for. And the height is 15. Okay, now we want to do some simplification. We'll keep that 462 by itself for now. And then let's simplify 1/3 and 15. That's just going to reduce down to 5b. And now we want to divide everybody by 5. And so our b is going to be equal to 92 and change. Again, not worth getting into the weeds. It's 92 and 2/5 if you're particular. Aha, I'm glad you're paying attention. Yes. See, it's easy to get into into the mindset of 2D geometry. Great catch. It is inches cubed for volume. But that, fortunately, didn't impact any of the math that we were doing. That was just a silly mistake. So we get the area of the base to be 92 and change, which is going to give us answer choice A. So this is one that's probably not quite as easy to wrap your head around in terms of ballparking out. Maybe you could have eliminated E as being way too big. Why are we multiplying 231 by 2? Because they're trying to trick us, because they're absolutely diabolical, and they snuck this 2 gallons in here. So they told us that 1 gallon is 231 inches, but we're trying to fit 2 gallons in there. So it's kind of a bummer if you didn't catch that. You could have worked through the steps of this problem beautifully using 231 instead of 462. But yeah, they just love to try to trick you. And that's why it's so important to keep your critical reading skills sharp as you're working through the math problems. And it can be hard because as far as I know, your math teachers aren't trying to trick you like this. I hope they're not. But they love to throw curveballs with these word problems, and so you've got to keep your guard up. Any other questions with how we did this one? Even if you don't have a lot of experience calculating stuff going on with pyramids, same as with the other questions, take the formula they give you, write it down, and try to piece together what you have. And sometimes that'll lead you in the right path to getting to the answer. Okay. So that's our 3D geometry one. Let's move back to basics here. And these types of questions, this is a number 1. This is what ACT would consider to be an easy question. These can be tricky in their own right because sometimes they're testing concepts that you haven't learned in years and certainly haven't thought about if you haven't done any sort of serious preparation before you take the test. So sometimes questions are hard because they're dealing with 3D geometry and there's lots of curveballs in the problem, and sometimes they're challenging just because it's something that you haven't thought about in a long time. And that's what can be tricky about what's going on here in question 1. So this one's got 4 railroad lines, A, B, C, and D, and they're pictured below such that the pair of lines A and B and C and D run parallel to each other respectively. So if the obtuse angle, see, it's another vocabulary lesson, created by the intersection of line A and C measures 110 degrees, what is the measure of the obtuse angle at which line B intersects line D? So everything's labeled for us, but we just want to take a look and see what's going on here. We're looking for the angle measure of where line B is intersecting line D. The obtuse angle, which we need to know, is the big angle. If you remember from back in the day, the obtuse angle is the big one and acute angle is the little one. And so there's some interesting rules that we can follow when dealing with parallel lines. And I'm just going to jot that down here. We've got the big angle, which is going to be the same when the lines are parallel and intersecting. So these are both going to be the same, and this little is going to be the same too. So whatever the value of the big angle is going to be the same. Whatever the value of the little angle is going to be the same. And on either side, no matter how you look at this, the big and the little are going to add up to 180 degrees because they're on a straight line. So here the big and the little add up to 180 degrees. Here the big and the little add up to 180 degrees. And so if you're kind of jumping ahead on this, we've got all the information that we need to be able to figure out what the angle measure of this one is. We don't even have to figure out what the little angle is, but if we wanted to, it would be 180 minus 110. So it would be 70. So we could just plug that in to make this complete. So 70, the littles are going to be the same, and the bigs are going to be the same. And that's going to correlate with all the intersections that we have in this very bizarre railroad. And so we can just make sure that we keep track of the big and the little angle, and we know that this unknown here is going to match up with the same big angle before, or 110. So our answer here is going to be A. Another thing we could have done here, again, if you're running out of time, if you don't remember these rules, ballpark out anything that looks like it's way too big. On these tests, unless it says it's not drawn to scale, you can assume that it is. So we could have eliminated these 3. Kind of hard to ballpark 110 versus 120. So we did need to remember that rule to be able to solve this question all the way through, but that's one way that you can eliminate some of your answer choices. Any questions with this one before we move on? All right. This one's a little more straightforward. Okay, so number 21, this one would be kind of in the middle in terms of difficulty. This would be a medium type of question on the ACT. In the figure above, AE is parallel or is equal to BE is equal to BD. EBD is 40 degrees and angle C is 45 degrees. What is the measure of angle A? So they drew us the figure, but they didn't label anything for us. So we want to make sure to put all that stuff down. So we know for sure that AE is going to be the same size as BE as BD. Okay, that's one thing that we know for sure. What else? EBD is 40 degrees. And angle C is 45 degrees. Okay, and we're looking for the measure of angle A. This is our unknown. So we've got to start somewhere. There's a lot of triangles going on in here. And so we want to kind of pick a piece of this where it looks like we have a lot of the information. And so I kind of am gravitating towards the middle one here because we see that these two sides are equal and we have an angle measure. So this is what we know as an isosceles triangle. So if these two sides are equal, that means that these two angles are equal. And we know that all the degrees inside a triangle are going to add up to 180. So we can figure out what these two angles are, and maybe that'll help us figure out what's going on over here. So let's figure out how we can do that. We know that all of the angles are going to add up to 180. And we've got 40 here, so we're going to subtract that out. So that gives us 140 to split between the two of those angles there. And that's we're just gonna divide that by 2. So we know that both of those are gonna be 70, right? So we got 70 here and 70 here. Okay. How is that helping us get any closer to figure out what's going on over here? Well, kind of like with the railroad problem that we just did, we know that this angle and this angle have got to add up to 180 degrees, right? So because they're on a straight line. So let's see what we can do with that. So we have 180 and we want to subtract out 70. So that's going to give us 110 for this angle in here. Okay, so that's one angle measure that we have for this triangle where we're missing the value for angle A. But we notice that we've also got the same situation going on in here, right? We see that these two sides are equal, which mean that these two angles are equal. And again, knowing that they all have to add up to 180, we can do that same math all over again, just following the same procedure here. So 180, we want to subtract out that big angle, and that's going to give us 70. And here's where it's really easy to fall into a trap, right? Because we see that that matches up with 70 degrees there. But we have to make sure that we're looking for what the question is actually asking. And we need to split that 70 between these two angles here. So we actually need to divide that by 2. So it's going to be 35 here and 35 here. So always be careful. They love to make answer choices out of intermediate steps of the problem because they think that you're likely to pick one when you've kind of done some steps and you feel like you've done a good job. But always make sure that you are answering what the question is actually asking for, and that's going to be answer A here. Which geometry concepts that the College Board lists would be useful with congruent sides and angles? Nothing advanced, really. Like truly, the thing that makes geometry questions difficult on the SAT and ACT is not the content level. It's the way that they give you these weird pieces and expect you to understand how to fit them together in a way that you're not used to dealing it. So knowing, your complementary angles, your supplementary angles, knowing the rule with intersecting parallel lines like we just did with the last problem, that's going to be sufficient to get you through most of the plane geometry. The difficulty doesn't come from high-level geometry concepts. It comes from these word problems and not noticing that there's 2 gallons and, stopping when you're halfway done with the problem. That's what makes these questions even more difficult. I'm happy to take any other questions, you guys, but this was the last geometry problem that I have for us today. So I'm so grateful that you were able to join us today and spend some time practicing for these tests whenever you're going to be able to take them. I hope it's soon if you like. We're always here to support you. We're here every week. I'll be back in a few weeks.